Okay, this is Dr. Casey Finnerty of the Biology Department at Winona State University, and today I'm going to be explaining how to um, analyze some data using formulae in Google Drive, and how to then go ahead and plot that data and compute a linear regression trend line for those data. And I'll be using as an example for all of this the template for the enumeration of bacteria report that is going to be used for students in microbiology for submitting their data on their exercise on this topic. And so the link that you'll be receiving, when you click on that link and open it up, you'll be looking at a page very much like the one you see before you on the screen. The one thing that you'll note is that if you try to click on this and type within it, you will not be able to, because it's a view-only document. And the reason why is I wanted to distribute the document as a template so that each of you worked on your own version of it. And so the first thing you'll need to do when you receive this link is to go up to File, and you click on that, and you just go down to Make a Copy and choose that, and you're going to enter a new name for your document, so that you'll be working off a copy of the version that was sent to you. And so very simply, I would just eliminate these words copy of, and at the end replace template with your first initial and last name. And so in this case, for myself, C. Finnerty. And so then once I've created that, I click OK, and you'll see that a new tab will open. In this case, this version of the document, you will be able to edit. So the first order of business that you need to do is to go ahead and enter the data that you collected from your laboratory, and that should have been recorded presumably in your laboratory manual. And the raw data that you collected was the number of colonies per plate for one or more plates from the standard plate count data, that part of the experiment. And then you recall that you then collected several absorbance readings at 550 nanometers using the spectrophotometer, and those data be entered here. To save time, I have a pre-filled sheet that we'll look at now on this tab right here. Okay, so for analyzing, let's take a look at this. You'll note that for the lowest dilution, meaning the highest concentration of bacteria that were plated, there were just too numerous, the number of colonies were too numerous to count, so I would just put in TNTC. And then we have a variety of colonies here, colony counts are entered for the other dilutions. And so if we want to convert from colonies per plate to CFU per mil, we need to multiply these colony counts by a conversion factor to bring it back up to what the concentration would have been in the original sample. Now for each of these dilutions, if we diluted it 10 to the minus 5 down to 10 to the minus 7 as you were instructed, then certainly we need to multiply it back up by the reciprocal of these numbers, so 10 to the plus 5 to 10 to the plus 7. And the easiest way to do that is just to go ahead and enter a formula in the spreadsheet. And so I'm going to click on this cell and then type in equal sign, which is the way of alerting Google Sheets that you're going to be entering a formula. And so then I'm going to select on this cell, and you notice it enters into the cell reference, in this case B10, automatically for me. And then the multiply symbol, which is a that asterisk above the number 8 on your keyboard. And then finally click on this cell. So it's going to be cell B10 times C10 as shown in this formula. And then I hit return, and it carries out that multiplication for me. Now I could go ahead and re-enter the formula for this cell and this cell, but the simpler way to do that is just to click on this cell, as I've just done, and then to move my cursor so I place the arrowhead over this little square in the bottom of the selection rectangle. And so if I do that, you notice that the cursor turns to an arrowhead, and I click and drag it down for 2 more cells, and it fills in the formula and then the correct answer to that formula for these other 2 cells. And just to convince you, if I click on one of these cells individually, if we go up to the formula bar, we see that it says correctly that this formula is equals B11 times C11. So it just took the formula from the cell above it, applied it to the next cell down, changing the cell references appropriately by going one cell down as well. Now, looking at these data, you can see that they actually look pretty good. First of all, in these last 3 plates, the colony counts are going down by a factor of 10, roughly 10 each time, which is what we would expect to see. Now, you may or may not see this for your data. If you're not seeing it going down by a factor of 10, you should ask yourself why that might be the case. There could be a variety of things going on. Perhaps you undercounted because the colonies are very small on certain plates, or perhaps your pipetting was in error. Perhaps your dilutions were made incorrectly. Perhaps you poured your plates, added your bacteria to the agar while it was still too hot, and some of the bacteria were killed in some treatments versus others. And so there's lots of things that you can consider and put down if you find that your colony counts are not going down by a factor of 10 from one dilution to the next. Now recall that the manual said that what would be a countable number or a statistically significant countable number. And in general, it was between typically 25 to 250 or 30 to 300. And so to come up with the best estimate, we might want to average a couple of these plates because we see that these roughly fall into that range, these last 2 dilutions. The other thing that, in terms of that range, the other thing I should point out is that, if these are indeed decreasing, these colony counts by a factor of 10, then the CFU per mil estimate, because the conversion factor goes up by a factor of 10 each time, the CFU per mil estimate should be about the same for every plate. So here we see it varies from, say, slightly below 3 times 10 to the 8th to slightly above 3 times 10 to the 8th. And so we see that the CFU per mil estimates are all in fairly good agreement. So let's go ahead and average these second 2 CFU per mil estimates because they are technically within that countable range. And so again, the easiest way to do that is to type in the equal sign and then type average, average. And then if we hit the parentheses, we can then select these 2 cells here and then hit close parentheses and then hit return, and there we have our average. So again, the formula is equals average, open parentheses, in this case D11 colon D12, that's the cell range that we've instructed it to average those 2 numbers in those 2 cells, and then close parentheses and return, and indeed it's calculated the average for those 2. And so if we want to go ahead and re-enter that number over here so it's easy to see, we just say equals and then type on this cell and hit return, and there you go. There it is again. So let's go ahead and we can say average of D11 and D12, just to make it clear to someone reading your report which numbers you averaged. And I've re-entered that value here as I've explained. All right, so as explained in the laboratory, now what we're going to do is use this direct number for estimating the CFUs per mil of that culture that was provided to you, and use that to convert from dilutions to concentration CFU per mil for that second half of the experiment, which was the turbidimetry data. And so you see over here the dilution factors, and the first one was 1 to 1, and then the others are roughly were 1 over 2, 1 over 4, 1 over 8, 1 over 16, and I've just converted those to decimals. In fact, if we just select on this one, you can see up in the formula bar, the way I did that was just by entering in equals 1 divided by 16 to get that decimal. And so now, similar to the way we did up here, we're going to take this CFU count, this average of 2 of those plates, and multiply it by the dilution factor in order to get the correct concentration now in CFU per mil so that we can create a standard curve. And so again, if we type equals to start the formula function, we could take this dilution here, which is the one, and so that's cell A22 on this spreadsheet, and then type the asterisk for multiplication, and then click on this cell here, B16, and hit return. And of course, the same number is returned because 3.28 times 10 to the 8th times 1 is indeed 3.28 times 10 to the 8th. Now, if you tried to do this same approach of clicking on the little square and dragging, you're going to notice a bit of a problem. And you could look at this now and you can see zeros for the rest of these wells or cells. You may ask yourself, why did that happen? Well, if you click on the formula on this cell, for example, and look at the formula, you can see that it took the correct cell reference for the first factor, A23, and that indeed is the correct cell here. But then for the second factor, it took B17, which is this cell right here below the estimated CFU per mil. And of course, that's an empty cell, so it's just basically taking this solution, multiplying it by 0, and giving you 0 as the answer. And so the question is, how do we make the formula change the cell reference for the first factor and not for the second factor up here? And there's a very easy way to do that. If we go ahead and click on this one in which the formula was correctly entered, what we're going to do is move up to the formula bar, and for the second cell reference, B16, which again is this cell right here, I'm going to enter in a little $sign between the B and the 16. And when I do that, that's going to tell the program that it should not change the row number when the formula is recalculated for subsequent cells. And let me show you what I mean. So I hit return, and now if I go back up here and I'll repeat that process of selecting on a little square and dragging, indeed, now the concentration is correctly computed for each of these cells. In this case, it's A23 times B16. In this case, A24 times B16. A25 times B16, and finally A26 times B16. So everything looks good there. Okay, so now that we have the concentration in CFU per mil calculated for our turbidimetry data, we can go ahead and create a standard curve using these numbers for the x coordinate and these absorbance numbers for the y-coordinate over here. And so the easiest way to do that is to click and drag across all these cells, including the headers, which will be useful in just a moment. And then to click on this button for the insert chart function. And before we do that, I'm just going to scroll this sheet up so we can kind of get a better look at things here. And now I click on insert chart, and this window comes up. And what do we see? We see that the range of cells looks correct, B21 through C26, so that everything looks good here in this box for the ranges. We don't need to switch rows and columns. We are going to use row 21 as the headers, because you can see there that that is row 21 with the headers. But the type of chart that we have here is not the type that we want. We would like to see a scatter chart. And so if we just click where it says recommended charts and we click on more, we can see there's the scatter plot right below. So we'll click on scatter plot, and then the type we want is the scatter chart in the first option. And so already you can start to see where the plot is looking pretty good. So far, you can tell that it looks like it's going to be a fairly straight line, which is what we're hoping for. Now, there's some things with this chart. If we just went ahead and clicked insert at this moment, you'd see the chart would be missing some very important things, like, for example, a chart title. Also, it would have no label for the y-axis or x-axis, so that would make it very difficult to interpret exactly what we're looking at. And so to enter in all these customizations, you want to click on this tab called Customize over here. And we can go ahead and enter in some information for the chart title and those coordinate axes. So for the chart title, we should say, let's see, absorbance of E. coli culture at 550 nanometers. You know what? I think a better name for this might be E. coli spectrophotometric standard curve. That sounds a little better. And it's going to be in bold. Now we should, I don't believe there's a way to selectively italicize E. coli. And so perhaps we could try, go ahead and try that, but I don't think it's going to work. Yeah, it'll italicize the entire thing. And well, what the heck, we can go with that too. And so now if we scroll down here, you get to the axes. So here we see the horizontal axis is currently chosen. The title, in terms of how the title appears, etc., all that seems fine, but we need to go ahead and enter into a title for what the horizontal axis is. And so in this case, we should put CFU per milliliter. And I think everything else looks pretty good there. And so now we're going to do the vertical axis or the y-axis and enter in the title for that. In that case, it is absorbance at 550 nanometers. And everything looks fine with that. And now as we get down here to scale, everything there is fine. But we do want to put in a trend line. And so if we click on the trend line option, the one we were looking for is a linear trend line, as you can see there. And once we've inserted that trend line, if you scroll down a little bit more, you can see that they give you some options. And so, for example, it gives you an option of a label. And so if we go ahead and select use equation, then we'll actually have the equation, the linear regression equation that was used to drive that line. And that is indeed what we do want. And then finally, we have the option of going ahead and inserting the correlation coefficient by checking this box there. Okay. And then I think having this OD at 550 nanometers is a bit redundant considering the fact that we have this y-axis labeled. And so just wondering if there's a way of getting rid of that here. Perhaps not. So maybe we'll just go ahead and leave that as it is. Full scale. Yeah, I think we'll just live with having that there, even though it's a bit redundant. All right, so then we hit insert, and there is our chart. And if we go ahead and grab it, we can move it down slightly so it's not quite overlapping our table, as you can see. And so when we look at this chart, it has all the requirements that I'd like to see met in your reports. It has a title. It has a label for both the y-axis and the x-axis. And then it has the linear regression equation with the correlation coefficient. So now, once again, in the future, if one would want to go ahead and use the spectrophotometer to quantify E. coli quickly and get an estimate of the CFU per mil, what you could do is take the culture, take an absorbance reading on it, and then plug in that value for y into this equation and solve for x. And so that would be essentially using this line to predict x and then solving for the CFU per mil. And so that's how you do a standard curve for this experiment. Finally, I should point out that the correlation coefficient you see here the R-squared value is 0.994. Again, if these points perfectly fit this linear regression trend line, this R-squared correlation coefficient would be a value of 1. And so this is very, very close to that value, and so it's obviously a good fit for the data. So once you've done this, you need to submit this in the form of a report, and the best way to do that is to copy and paste this material into a word processing document, and so we can do that right now. Notice that I've put in the names of the students participating in this report. You should do the same, and then let me show you how to go ahead and create a report by copying and pasting these data. So first I'm going to select the two tables of data as well as the student names and the title like you see here. And then you're going to need to use your keyboard and enter Control-C to copy that selection of your spreadsheet. And then we're going to go up to File, New, Document, and a word processing document will open up here. And then to paste, we're going to do Control-V. And you see that those data and those tables now have been entered into your word processing document, and everything looks pretty good. I'm going to enter in a couple of spaces here to create some room, and then of course the next part that needs to be entered is that table. So if we go back to the spreadsheet tab, as we see here, if I just hit escape, that should undo that previous selection, and now I'm going to select the chart by clicking on it, and again hitting well, actually I think the best way to do that is to pull on this little drop down menu, and then if we just hit copy chart, that would be good. And now if we go down to this tab here with the word processing document, I can just do Control-V, and there's the chart showing up in the report. Now, the final thing that I would like you to put into your report is just a brief discussion. And so we can go ahead and enter in a discussion. I just chose a nice heading style. And a couple of things that we can say about this. First was the standard plate count data was reasonable. Colony numbers varied by a factor of 10, indicating that by a factor, let's say by a factor of 10 as expected, indicating that the dilutions and procedure was performed correctly. The 10 to the minus 6 and 10 to the minus 7 plates had colony counts that fell within the 30 to 300 range, so their CFU per mil estimates were averaged. Okay. And then in terms of analyzing your turbidimetry data, we could say that plotting a standard curve of CFU per mil versus OD at 550 nanometers yielded a linear regression line and our, let's see, can we do superscripts in this? Let's see. Let's see, our format, here we go, superscript, R squared, and now clear formatting, value of 0.994, which demonstrates that the data fits the regression line quite well. This standard curve could reliably be used to estimate bacterial density in a broth culture. And that's pretty much it, what you need to do in terms of a discussion. You don't really need to do much more. Now, of course, if your data don't look good, you need to say so and come up with some ideas as to how you might improve things if they don't fit the trend line very well, or if not all your plates were countable, things like that. And so again, we don't expect perfection in terms of results the first time you do it. But we do expect you to be able to recognize when things don't look right and come up with ideas as to how the experiment can be improved so that the next time your data would look better. So that's pretty much it in terms of how to use this. Once you generate a report like this, you need to submit it, obviously, and again, make sure that your names are on it. Now, each student needs to submit his or her own report, and so in the Dropbox that was created for this assignment, you need to each submit your report. And the best way to do that is to go ahead and once you've created this document, we need to come up with a title for it. And so if we do enumeration, how about this one? This is better. Bacteria Enumeration Report. And again, putting in first initial, last name. We can now save this as a named document. And from Google Drive, you can hit File and then Download. And go ahead and download it as a Microsoft Word file. And when you do so, that document will be downloaded to your Downloads folder on your computer. And that document can then be uploaded to the appropriate Dropbox that was created for this assignment. And so please do that by the posted deadline. And if you have any questions, feel free to let me know. Thanks a lot. Bye.